This week, it's going to be a great pleasure to hear from Ilya Svetlizky. I hope you saw the formal announcement by email, because I'm not, it's been our habit not to have a formal announcement at this point, to make this informal. Our normal mode of operation is to simply ask you to put yourself on mute initially, but normally it's fine to interrupt with points of clarification, and then to wait, because we will have a nice extended question and answer and discussion session at the end. And whether you've been with us normally or not, I really want to encourage people to be prepared to participate in the discussion, mainly because I think it's interesting, but also because let's remember that Ilya is giving a seminar in his office or somewhere by himself to his screen. And so that's a pain. But one of the, let's say, benefits could be that we have a chance to have an extended discussion, because people can leave when they need to. And I think that is a nice benefit about this seminar series. So please be prepared to participate in that. Ilya, thank you very much for being here. I'm going to turn the floor over to you. And thank you.
Thank you, Chris. So I guess you see my slides, right?
Yes.
Thank you, Chris, for this opportunity. It's really nice. I want to tell you a short story. So imagine you have a crack. Maybe it's a very slow crack, maybe even creeping crack. And the story will be that if you take a very careful look at your creeping crack, it seems that sometimes you can find very intricate, fast dynamics. So this is the story I want to tell you. The work was done during my postdoc at Harvard. There is a long list of co-authors. Let me point some out, some names. So Dave Waits is the mastermind. He has been thinking about this problem for some time now. Thomas Koshard is actually the guy who was leading the project, and he did all the experiments that I'm going to show you here. And I will show you some really amazing simulations were done by Gabriele Albertini, and Rob Vieska and I were around to help with the analysis and fracture mechanics modeling. So, okay, 1 second. Okay, so I apologize for preaching for the choir. So really short introduction. It's obvious that the question, how do things break, has a lot of implications, both engineering, and of course, it's intimately related to earthquakes. And this is the last picture you'll see in my talk about earthquakes. But I also find fracture interesting for just for the basic reason. Now, people have addressed fracture mechanics or cracks for a very long time. And let me define that the crack tip in quasi 2D samples is a point. The point separates the intact material on the right to the broken one on the left. And in 3D, the crack front is no longer a point, it's a line. And what makes the 3D fracture interesting is that the crack front can curve. It can curve in and out of plane. And it induces a lot of challenges, both from theoretical perspective and from experimental perspective. So Jay Feinberg and his group and other groups around the world have addressed the 2D fracture, and we have quite a lot understanding. We have a very good description of how cracks in quasi 2D propagate. The challenge in 3 dimensions is to model the variation along the crack front line. And from theoretical perspective, the math getting very, very ugly. And from experimental perspective, the challenge is first to be able to visualize in 3D the crack front. And second is to do that fast enough so you can capture the dynamics. So in this talk, we consider a very specific geometry where we have a penny-shaped crack driven by injecting a fluid. So as I said, Thomas Cochard did the experiments. What he was able to do is to 3D print an optically clear sample with initial penny-shaped crack. Then, by injecting the fluid at very, very slow rates, takes a couple of minutes to fill up the whole sample. And the crack will initiate, or the crack will start running once the pressure reaches something like 50 megapascal. Now, the control parameter is the viscosity of the fluid that we are using, somewhere between water, 1 centipoise, to almost 800 centipoise. And the most crucial part is that we visualize the dynamics of this crack by using extremely high frame rate, about 100,000 frames per second. So this is a snapshot of the measurement that Thomas acquired. We subtract the background, so you only see the changes. The first circle is the propagating crack front. The second circle is the expanding fluid front. Now, the fluid lags behind the crack, and when I first saw this observation, I was very surprised, but actually people are well aware about the fluid lagging the crack for some time now. It has been observed experimentally. It was considered both numerically and analytically. But as far as I know, or as far as we know, we are not aware of any dynamic study of how these things behave. So this is an example of an expanding crack. The crack runs, the fluid lags behind. I hope you see the movie. And the first thing that I want you to note is the fracture front is discontinuous. It jumps and then it stops. The pauses are very, very long. The second thing is the fluid front is actually very continuous. It expands, and importantly, there is the injection rate is really, really, really slow. So whatever you see now is only happens due to the expansion of the compressed fluid. And the third thing, which is the most interesting in our opinion, is that the radial expansion of the crack doesn't take place uniformly. Rather, it nucleates at some point and then expands in a transfer direction extremely fast. Okay, so these are the three observations that I want you to keep in mind. And the rest of the talk, all I'm going to do is to try to convert these nice movies into science, okay? Just to provide some detailed analysis of what you see on the screen. So we can take, these are two, on the left you see two snapshots at 2 and 4 milliseconds. Whole experiment takes about 5. We can track the crack front, this is red. We can track the fluid front, this is blue. And a nice way to visualize the dynamics is to take a single radial direction and plot the intensity along the radial direction versus time. So this is the plot. Again, the red indicates the crack front, the blue is the fluid front. And what you see is that the slow motion, so the average motion of the crack is pretty much the same as the average motion of the fluid. It's really slow, about 3 meters per second. But unlike the fluid, which expands continuously, the crack jumps very rapidly with very long times where there is no motion at all. And along the talk, I will use lambda to denote the lag size. This is the lag where the fluid lags behind the crack front, and the jump amplitude of the crack, which is delta lambda. So as I said, we have a control parameter, which is the viscosity. So the previous experiment was at 400 centipoise. And now I'll show you a movie, what happens when you just use water, 1 centipoise. And when you run the experiment, what you see is that there is almost no lag, or it's very difficult to find any lag between the crack and the fluid. And it seems like very smooth motion, but if you're careful enough, even the 1 centipoise has some dynamics along the transfer direction. So again, we take a couple of snapshots, we track, we plot the radial intensity along versus time. You can see the 400 centipoise big jumps, large lag. There is no lag, there is almost no jumps with pure water. And just to fill up the gap, this is an intermediate example with 100 centipoise. And what you see is that the jump size, delta lambda, increases with increasing lag. And the lag by itself increases when you increase the viscosity of the fluid you're injecting.
Ilya, it's Chris. Sorry, I've got a dumb question. So you have the injection rate is constant, and the fluid rate is, yeah, so it doesn't show the same jumps, at least at 400 centipoise as the outer position, but the blue line is not straight either. And that's what, the pressure building up in the crack?
So the injection rate is constant, but it's really, really, really slow. So during the experiment of 5 milliseconds, there is no fluid injected by the pump.
I see.
What happened is that Thomas was able to load or to compress the fluid. It reaches 50 megapascal. So before the crack starts propagating, before it nucleates, the fluid is actually compressed. So the motion of the fluid is purely the decompression of the fluid with some contribution also due to the elasticity of the tubes and the medium itself. But the pump is irrelevant at this moment anymore.
Gotcha. Thank you.
Ilya, sorry, that is Massimo. But following this, this means that your injected volume is not constant.
It's not constant versus what? With different viscosities.
Yeah, but if you have a given viscosity, you maintain a same rate of injection. But because here I see that even in this case, for low viscosity, you don't have any straight line of advancement. How scale the injected volume of fluid in time?
So injected volume in time. So I'm not sure that I'm following. There is no injected volume, any additional injected volume during the time the crack runs. So you always start with the same crack. You fill up the crack with fluid, and it nucleates. And during the time the crack runs, there is no additional injected volumes. Maybe I didn't say, so it's a syringe pump. It means that we control actually the displacement of the pump. We don't keep the pressure of the pump constant. This is almost impossible to do at milliseconds, right? So we control, it's a syringe, high pressure syringe, where you control the end part of the syringe. So basically the volume, the injected volume, and then the fluid is just decompresses. And it's a delicate question. You can ask how much of the fluid is actually inside the crack, how much of the fluid is inside the tubes, how much the tubes were expanded, all these details we worked out, but they are not contributing much. So what we don't really understand is why different viscosities give you pretty much the same expansion rate. So all of the experiments run about 3 to 10 meters per second. And this is a result that I'm not sure how to explain. Does it make sense?
Yeah, thanks.
Okay. Okay, and yeah, injection rate, the expansion rate is not constant. At the beginning, the fluid expands very, very fast. So this is the high slope, and then it slows down a bit. But it's a radial crack, so I think I guess it makes sense. The larger the crack, the more volume, differential volume you are freeing for every delta R, right? Okay, so we can sum up all the measurements, different viscosities. The left figure plots the jump amplitude, delta lambda versus the lag. So as I said, the larger the lag, the larger the jump amplitude, and the lag grows with the fluid viscosity mu. So these are the two results that I will start with giving a very simple model to make sense what you see on your screen. So again, I apologize. I will touch base quickly on the theory, the basics of brittle fracture theory. So imagine you take an infinite medium. You have a crack, you apply some tractions, and what is amazing about the linear elastic fracture mechanics is that it predicts a universal behavior around the crack tip. So the stresses diverge like 1 over the square root of R. R is the distance, radial distance from the crack tip. Now, in nature, there are no singularities. So obviously, the very high stresses around the tip are regularized at some region. Where usually, it's called the cohesive zone or the process zone. And the brittle theory describes cracks where this length scale of the process zone is much smaller than any other dimensions of your system, basically. Now, the only dissipation takes place at the crack tip. So you have all the energy, the elastic energy that goes into the crack tip is dissipated there. And you can rephrase this energy balance, saying that the crack will propagate only once the stress intensity factor K is the prefactor of your stresses, equals or larger than Kc, the critical value, sometimes called the material toughness. Now, there is an important velocity scale. Typically, cracks accelerate and reach the Rayleigh wave speed, something like 1,000 meters per second for PMMA. This is the plastic that Thomas was using. So the behavior around the crack tip is universal. The prefactor K is not. It's determined by the specific geometry or the specific loading conditions that you use. For example, if you imagine a uniformly pressurized crack with initial length B, the stress intensity factor will be proportional to the pressure you apply, and it will increase like the square root B, the square root of the length of your crack. So what you need to think about is that you start with some seed crack with initial length B, you increase the pressure, the stress intensity factor grows, it reaches the critical value, the crack starts propagating. As the crack grows, K increases, so you have excess of elastic energy, and all this excess K larger Kc goes to acceleration of the crack. Good. A different scenario is that if you imagine point forces loading, so again, you have initial seed crack with a length B, you apply point forces. In this case, the stress intensity factor K will decrease as the square root of the length. So again, you start with some initial length B, you increase your point forces until the K reaches the critical toughness, the crack will start propagating, but this time, as the crack propagating, K is decreasing, and in order to keep the crack propagating, you need to increase your forces, meaning that the velocity of your crack will depend on the loading rate, or how fast you increase P. Okay, so this is a theoretical analysis. The first case is well established and it works very well. The second case doesn't go according to plan. So this is a result. the late 80s by Ravishankar and Balzano, where they took a sample under tension, they applied displacement at the two ends of the sample, and what they found is that they were able to measure the stress intensity factor, this is the top, and the crack position on the bottom. So what you see is that as the time goes up, the stress intensity increases, it reaches some critical value, and then it drops at the time that the crack jumps. When you want the next jump, you need to keep on increasing the stress intensity factor. Again, it jumps and stops between the two values of the stress K. So there are two values. There is the critical one for nucleation, and there is the critical one for an arrest. And this ratio is about 10%. So keep this in mind. So now what I want to do is to take the same analogy and apply it to our fluid-driven crack. So there's a couple of notations. The crack length, the radius of the crack is R. The fluid front denoted by RF. The lag is lambda, and the crack opening is W. So we can write the stress intensity factor for a penny-shaped crack. And let me stress now that we are ignoring any transfer dynamics that I was pointing out earlier. So it's a pure circle, and it expands like a circle. The stress intensity factor is given by this formula, where you integrate the kernel is the pressure that applied, and solving both the crack and the fluid is extremely difficult to do. There are a couple of solutions for self-similar expansion. There are some key figures in the literature that know how to solve them. So what we decided to do is basically to ignore the fluid. And the justification for that is that the jump of the crack is so fast that we assume that the fluid front is stationary and doesn't move during the jump side. So what we do is we basically assume that the fluid is stationary, and we only need to specify the pressure profile that the fluid applies on the crack faces. And if the flow is very viscous, you would naively assume that the pressure profile has to be linear. If the viscosity is very low, the pressure can be almost constant. You take these two limits, and it doesn't make any big difference. The key point is, again, is that if we plot the stress intensity factor versus the lag, we see these functional form, decreasing value. So the larger lambda, the smaller k, very similar to the point forces that I described. But importantly, if we assume the same observation that Ravishankar saw, that delta K, the difference between the nucleation toughness and the arrest toughness is roughly 10%, this figure suggests that if your lag is larger, for the same 10%, you would get a larger jump of your crack, right? So this is the x-axis. And if you plug the numbers, the framework explains reasonably well the amplitude of the jump versus the lag. Please do ask questions. I'm running very fast.
Ilya, can I ask you? So the assumption, so the fact that the poor pressure profile with space is linear is an assumption, or it is a result of the model?
No, this is a pure assumption. I don't, in order, this is why the problem is so complicated, because what you need to do is you need to solve your crack, and then you need to adjust the pressure and solve the pressure self-consistently with the elastic medium. So you need to couple the fluid with the elastic medium, and to do that, I don't know how to do that. There are solutions by any means we tried, we were not able to utilize these solutions to our case. So what we decided at the end of time, just out of being desperate, is to say the simplest thing: we will take some scaling. P is either linear or constant, and these are not they are not so stupid assumptions. These solutions that I told you about that we were not able to utilize do show that there is a continuous transition between something that looks very linear to something that looks very, very, very constant just before the crack tip. So this is the pure assumption, and this is the best I can do. Importantly, if you, again, just let me stress, if instead of a linear profile, you take a constant profile, it doesn't make any difference. Or it does, but you will not be able to see a big difference, okay?
And did you try to have an increase of the pressure, actually a decrease of the pressure from the fluid front to the crack tip, which is nonlinear?
Sorry, I'm assuming that here is a vacuum. So the pressure between the fluid and the crack is negligible. This is my assumption. You're absolutely right that near the fluid front, there is strong non-linearities of the fluid pressure that we didn't incorporate. So again, as I'm saying, these non-linearities are localized, and our assumption that will be smeared out by this kernel. So we took the two limits, constant and linear profile, and didn't go further into detail. I think this is almost scaling argument. So if you want to do better, you somehow need to solve that, and I don't know how to do.
Yeah, sorry, I misunderstood. So now I understand what is the hypothesis. Thanks.
Great.
Ilya, may I ask a question? It's Elsa.
Yeah. Hi, Elsa.
Then in your model, not model, but here you assume that you have the same thing than Ravi Chandar, that K arrest and K initiation are different.
Exactly.
But
is the
do
key
they understand from where it come from? Is it like specific to their system, or is it something general? Can they model it?
I don't. I guess Jay will have an answer. I was trying to keep up. The paper I'm specifying here actually made the point that this stick break or stick slip behavior is not a material property, it's a loading property, because before the 80s, people have thought that specific materials have stick slip, others don't. So Ravi Chandar demonstrated different polymers show pretty much the same behavior. Now, whether metals or rocks will show the same difference, I'm not sure. So it might be something very intricate related to grazing of the polymers, but I don't know how to explain. What I have in mind is, it's not a model, but what I have in mind is, or something that I wasn't able to rule out, is the fact that usually these materials are viscoelastic, so there are different timescales involved. You nucleated some. Before your nucleation, you have very long time behavior of viscoelastic material. Once the crack runs very fast, maybe short time dynamics or short time viscoelasticity plays a role. So maybe this difference, but I don't know a microscopic mechanism to explain it. Hopefully, it's not only a polymer thing. I think this difference usually, because it's so minute, it can be overlooked in other materials unless you do exactly the same experiment. So observing 10% difference, unless you know what you are looking for, is very, very difficult. So I hope it's not a polymer thing only.
Okay, but you're confident that in your system, because it's the same material as Ravi Chandar, you do have the 10% as well. That's what you
we use 10%, but frankly, the way I present that, it's not the way the study went. We first figured out the process. We guessed, fitted the observation with 10%, and by accident found Ravishankar saying, this guy saw the same 10%. This is cool. I'm not sure it's the same. I'm not sure what material he was using. Maybe it was homelite. I'm not sure if it was exactly the same PMMA.
Okay, thank you.
Ravi's experiment, not that I know anything, you gave me too much credit, Ilya, but it's not point loading on the crack faces. So you have some combination of elastic volume loading plus something that's like point loading. Whereas in your experiment, this is exactly the scenario that your expression for the stress intensity factor is made to answer. It's the loading is exactly on the cracked faces. So
yeah, you're absolutely right. But the difference, what Ravishankar did, what Ravishankar was controlling is the displacement. He didn't control the force. But I think you can map those to each other very easily. The idea is that once you apply either displacement or point forces, once the crack propagates, it decreases the stress intensity factor. In both cases, it's the same. I feel it's very similar. Quantitatively, it might be a bit different, but
you don't
I
think
think
it's
about them
that
the same.
relevant?
Well, we use we in our
just...
model, as you say, we use the expression for the point forces to integrate the kernel, but the phenomenology, I think, what I'm trying to say is that if Ravishankar was applying a constant force, I think he would also get stick slip. Okay, if he would just hang up a mass here instead of controlling a displacement, I think he would also observe stick slip. This is the point I'm trying to make.
My guess is that this is all I'm going to say is that it has something to do with creep at the crack tip. So the sharpness of the crack tip is, and that's why you're seeing exactly the same thing in both of these, and if it's more or less the same material. Your
the sharpness jumps, of the crack tip, yeah?
Yeah, your crack jumps, it has a very sharp crack tip, and now you're reloading it. And you're giving it time to creep a little bit, so the process is changing.
I should have reached out to you to talk about that. I was thinking about it for very long. So the initial crack that Ravishankar induces is not sharp. This is why the first point is indeed higher than the other ones. But once you created a sharp crack, and once the crack stopped, I'm not exactly sure why the crack will be blunted after the arrest, unless you have some smearing due to viscoelasticity or something like that.
Plasticity near the crack tip, I'm guessing.
Yeah, great. So this is the mechanism that Elsa was looking for. So I was right, if you know.
I'm going to shut up now because I've told more than I know, which isn't that much anyway.
Good. So the next step is I want to give some sense why the lag between the crack tip and the fluid front depends on the viscosity. So again, a heuristic argument, you have a Poisson flow. Poisson flow is that the average velocity of the fluid times the crack opening is the flow, depends inversely on the viscosity mu and depends linear on the pressure gradient. Again, this is the scaling arguments. You take your pressure to be linear with pressure, the gradient of the pressure scales like P over the radius of the fluid front. You again rewrite the stress intensity factor in some useful form where the integral is non-dimensional. So you have one part that increases linearly with P and an integrand that goes is monotonic, and it increases to 1 when the fluid front equals to the radius of the crack. So RF divided by r equals to 1, this integral goes to 1. You compare the stress sensitivity factor to a one value, Kc. Again, these are only 10%, so I'm ignoring any difference between initiation and the rest at this point. And the argument is the following. For some reason, as I indicated, the fluid flows pretty much at the same rate, regardless of the viscosity, something between 3 to 10 meters per second. So if you take V be constant, what this equation means that the higher the viscosity is, the higher pressure you need to drive the fluid, which sounds trivial. Now, if the viscosity is higher and you need larger pressure, this part increases. But in order to keep the K constant, the integral should decrease. And the only way for the integral to decrease is to increase the lag. So the more viscous, you need the higher pressure to apply. Higher pressure you have, the larger the lag you should get. So you plug the numbers, and I think you get a good result relative to the simplicity of the model. Okay, so up till now, we ignored any transfer dynamics. So I assumed in the simple model that the crack expands like a circle. So it's a penny-shaped crack. And so let me switch gears and now try to explain the transfer dynamics. So we subtract the first image, focus on a single event, on a single jump. So the rupture nucleates at the top left corner. It starts propagating clockwise and anti-clockwise, and at about 100 microseconds, it completes the whole circle. So the forward mechanism is that rupture nucleates and expands through a very rapid transfer expansion. So this is how you start with the circle and you finish up with the circle. And we can track the crack front. So these are the colors correspond to different time steps. The y-axis is the radial expansion. The x-axis is the coordinate along the periphery of the perimeter of the crack, r theta. So it seems like the crack sticking out a nose, out, and then expands in the transfer direction. So to quantify that, we can define two velocities. One is the radial expansion, and the second VR, and the second one VT is the transfer velocity. So we track the velocities. This is the y-axis, x-axis is time. And what you see is that the transverse expansion is really, really fast, reaching the Rayleigh wave speed, whereas the radial expansion is really, really slow. It starts about 200 meters per second, but this is an underestimate because we don't really, our time resolution is only 10 microseconds, right? But anyway, during the most of the expansion of the crack, the radial velocity is really, really, really slow. And just to remind you, this is delta lambda, the jump amplitude. You plot the tangential velocity versus the jump amplitude. And what you get is that for large jumps, the transfer velocity approaches the Rayleigh wave speed. Whereas as the jump size decreases, you can reach almost half of the Rayleigh wave. So we were very curious about this result for some time. We put some amount of effort to try to come up with a model to explain how cracks expands in a transfer direction. We are not aware about anything like that in the literature, and pretty much when we gave up, we went begging for help to Gabriele. So Gabriele has amazing capabilities. He really knows how to do top-notch numerical simulations, and we were lucky that he was around at Harvard at the time. So we came up with to Gabriele, okay, let's simulate our experiment. So the first thought is, of course, let's simulate the crack and the fluid, which comes out, again, very tough job to do. Simulating both requires a lot of effort. I think there is, I think there are only a couple of groups in the world that actually do that. So again, following our analysis that I showed you before, we said, okay, let's ignore again the fluid and mimic the fluid just by applying, mimic the fluid by the pressure it applies on the crack force. So the setup that Gabriele did is a linear elastic medium. It's a brittle crack. The cohesive zone size is finite, but very small, at least relative to the lag. The pressure is prescribed. I think Gabriele took a constant pressure profile, but it doesn't really matter. And the key idea is that he induced non-uniform profile of the material toughness, meaning that before the crack, the Kc is larger than the stress intensity factor, which implies that when Gabriele sets up the simulation, the crack is stationary, it doesn't move anywhere. Now, right after the crack, the Kc drops, and of course, the problem is three-dimensional. It's a planar crack, a straight front, so we ignore the circular shape. It's not really important. And in order to induce the crack, Gabriele nucleated it by decreasing the strength of a small patch. So this is a really crucial point. You reduce the strength of a material very locally, and once the crack nucleates, it expands in a self-sustained manner. And the control parameters are, again, either or both the applied pressure and the jump amplitude. So this is a movie of this simulation. The x-axis is along the crack line. This is the crack, the crack front. It's a straight line. When I start running the movie, what you see, the crack is nucleated at the middle. It jumps and starts expanding in a transfer direction. And at this moment, you cannot stop the crack. It's self-sustained. So this looks very promising. We tracked the crack front of the simulation, and well, it looks. I think it looks good. It shows the same phenomenology. The crack jumps at the beginning very rapidly in the radial direction, and then stops and expands in both to the right and to the left. And you track the velocities. The solid lines are the simulations. It tracks well both, it reproduces well both the tangential velocity and the radial velocity. So this is great. The simulated fracture fronts match the experiments with a specific caveat that these simulations mimicked very large jump amplitude. So the comparison I showed you happened about 2 millimeters of the jump amplitude. Interestingly, the simulations fail to describe the really, really small jump amplitude. So as the jump amplitude increases, works well. At smaller values, it fails. So we don't have an answer. I will give you two options. So what is the origin of this discrepancy? Why the brittle theory doesn't work very well at very small amplitude? So one naive answer would be, well, you neglected the motion of the fluid maybe when the fluid is very close to the crack, some weird interaction between the two slows down the crack dynamics. So I don't know how rule out this option. But what we do have, there is a good evidence that maybe not the interaction, but actually the brittle fracture theory fails. So we have some evidence that when the jump size is comparable to cohesive zone, the transfer direction starts to slow down. So I'm not showing you these results. These are preliminary. I hope we will get them out soon. But we do have simulations where the amplitude is comparable to the cohesive zone size, and the transfer direction slows down. So I think it is a good indication that maybe the fluid crack interactions are second order, and really what fails is the assumption of the brittle theory. Now, the jump amplitude here is about several hundreds of microns. To measure the cohesive zone size in our experiments is not so simple. There is some evidence, and again, Jay maybe can correct me, that people estimate the process zone in PMMA to be some order of 100 microns. So I think it makes sense, although I'm not sure if the printed PMMA behaves like any other PMMA.
Yeah.
So yeah,
It's Chris. I missed why you don't have simulations for these very small jumps. Is it?
So I'm not presenting you. I just didn't catch up with Gabriele. So this is the published results. In all these results, Gabriele did a lot of effort, made a lot of effort, so that the brittle theory holds, meaning that the jump size is much larger than the cohesive zone size. By accident, we found out that it might be not the case, and we just when it's not the case, it slows down. But the exact analysis we are still working on. So I'm not sure if it will reproduce our results quantitatively, but at least qualitatively, we know that when the cohesive zone in the simulation is comparable to the jump size, the transfer velocity slows down.
Gotcha. Thank you.
Okay, so this will be my last couple of slides. I want to show you some cool stuff about a bit more complicated behavior of the crack. And to do that, I will show you a movie where this time we are subtracting two successive images. So basically taking a derivative in time. And what the movie shows is that this transfer behavior is a bit complicated sometimes. Sometimes you have a single nucleation and propagation clockwise and anti-clockwise, but sometimes you actually have several nucleation events simultaneously. Sometimes the cracks nucleate and annihilate, or keep on rotating. So let me put that into some way that you can actually see something. So when we decrease the viscosity, these are first evidence that you have two simultaneous nucleation events. You have first nucleation event happens, and the yellow crack propagates to the right, clockwise and anti-clockwise. Traverses something almost half of the perimeter. A second nucleation event takes place, and these can meet. So when the transition happens between single nucleation to two nucleation and more, so it's easy to compare the timescales. So you can think about an average velocity of the crack. It's pretty much the average velocity of the fluid, and it's equals to number of jumps times the jump amplitude divided by the number of events times the waiting time between the two events, meaning that the time per event is simply the jump amplitude divided by the average velocity. Now the transfer propagation, this is the time for a crack to finish half of the circle is pi r divided by the transfer velocity, which is pretty much around the Rayleigh wave speed. So you would expect simultaneous events when the transfer time scales getting larger than the time per event. And this happens when the delta lambda gets smaller and smaller. And we know that delta lambda gets smaller and smaller when the viscosity goes down. So when you decrease the viscosity, you get more and more simultaneous events. So this is another example. You have event 1 and 2 nucleated sometime before the image that I show here. They meet and they annihilate. At the same time, 3 and 4 are nucleated. They meet and they annihilate. So this is an example for annihilation of coexisting crack fronts. And this is an interesting example that I'm not sure that I entirely understand, is that somehow the dynamics break the symmetry, and you have only clockwise rotating rupture. So one follows 3, 3 follows 2, and they just run across along the perimeter. So this is one centipoise in water, where I told you that it seems like smooth motion, but it's actually never a smooth motion. What seems like a smooth motion takes place through multiple simultaneously propagating cracks. So let me finish with a caveat. Or not a caveat, just bring it into some context. There is a long discussion in the literature about crystalline materials and something that is called lattice trapping models. So people have considered cracks propagating or efficient way for cracks to propagate. And this is very similar to dislocation theory for those who know. So you start with a straight line. It's a very efficient for a crack to break a single atom, to stuck because you're trapped between the interatomic potential, and then you just expand your crack to the right and to the left until you just broke all your atoms. So these have been considered both numerically and theoretically. Our models, the jump in our measurements is no way close to a single atom. So this is a bit different animal, but very, very, very same of the same taste. So let me conclude. I think one of the surprising parts for us is that fluid-driven fracture can be unstable. And to our understanding, this hasn't been explicitly said in the literature. So every time, or many of the times that you see a slowly propagating or creeping crack, it actually can involve very fast dynamics. And the second point is that these dynamics take place through a very specific mechanism, where the radial expansion is nucleated in some localized region, and the circle expands by transfer cracks that run along the transfer direction. So thank you very much for your attention.
Ilya, really wonderful talk. I will invite people to turn off the microphone, join me in thanking Ilya. Okay, and yeah, let him catch his breath for a second, and then the easiest approach is to use the reaction button at the bottom of your screen to raise your hand like this, and put yourself in some order to, I don't know, have a discussion, ask questions. Absolutely want to encourage everyone to join into the discussion, questions, comments, and other things. And yes, I will thank Nick Brantu for going first. Nick.
Hello, great talk. Thanks a lot. Have you These experiments remind me of what people have done when they were looking at stress corrosion cracking in minerals and crystals and even single crystals. Because when you use stress corrosion cracking, it's very, very slow average crack propagation rates, like 10⁻⁹ meters per second and so on, but you still get acoustic emission rate. And the acoustic emissions rate is proportional to the crack growth rate on average. So do you think there's something at play that could be similar here, or should we look at something else?
I totally agree. I think I hope our results extend beyond the fluid-driven fracture. And as I said here, I'm not familiar very well with crack erosion, but it seems what you described now, if the crystalline material if the crystallinity of the material is important, so these are the models that exactly try to explain why creeping cracks in single crystals can propagate very, very, very slow. And the argument was that you jump atom per time. This is the idea. So I think it's very similar. I'm not aware about direct evidence of visualization of this process, unless, as you say, it's obvious that people probably measure acoustic emission. This is true. You are absolutely right.
Okay, thanks.
Elsa, please go ahead.
Hi, me again. Thanks a lot. It was great. About the simultaneous propagation of ruptures, how does it work actually? Because you already broke some part of the interface. Then what does it mean that the next one would break a little bit further the material?
Yeah. For example, here, imagine that at the beginning you have a good circle. So it's good good assumption. You start with a very nice circle. You nucleate at some position, so it's no longer a circle, right? So it's a circle with some kink into that. And what happens is that in this region, and the nucleation event number 2 takes place at the other part of your crack that hasn't been broken yet by event number 1, right? So so now event number 2 nucleates, and you get 2 cracks. And the extreme case here is that your radius of your circle always increases. So it's hard to see in these 3 images, but obviously between the 3 time steps, the circle on the right is larger than the radius of the circle on the left. And the radius increased through this constant transfer motion of these cracks. So this is the idea.
Ilya, did you want to follow up? I'm sorry, Ilya. Elsa, did you want to follow up?
No, it's fine. Thank you.
Yeah, beautiful. Thank you very much for a really fabulous talk, Ilya. I'll just ask one quick question and then pass on here because I see other people have questions. But yeah, so you have these distortions that are interesting and clear. And did you also see feathering or fingering so that there were a series of cracks at the crack tip? Or was it always just one crack?
Series of cracks at the crack tip? You mean out of plane? What do you mean?
Yes, out of plane. A series
out of plane.
Branching.
Yes. So this is really cool. You're absolutely right. Unfortunately, I don't have the images of the crack surface. The crack surface, when you look at the crack surface, and Thomas did a lot of work on trying to quantify the crack surface, they are not entirely smooth, and they have signature of circles where the crack had stopped. And for some time, we thought this is intimately related to Jay's crack fraud. So Jay and others have worked on crank front waves, where the waves have some out of plane contribution, which leave a mark in your plane. I think it might be similar. Maybe this is the mechanism that makes the difference between the KC for nucleation and KC for arrest. So the flat surface, crack surface is not flat, it clean signatures, but we were not able yet to make science out of that.
Yeah, that's cool. It reminds me of, I'll send you some pictures at some point. It reminds me of some experiments we did several years ago at Penn State with Derek Ellsworth. And when we used supercritical fluids, there were always this incredible distortion of the crack front, and it broke into a bunch of different surfaces. Which we never really had a good theoretical understanding of, but it's pretty clear. I need to look at some of your recent work. So, thank you. Sungshin, please go ahead, Sungwin.
Hi, Ilya. Thanks for your talk. And I just have a simple question about how do you consider the surface energy of the liquid? Like if the liquid is not, or the wetting properties of the liquid insert to the interface, because I suppose if it is hydrophobic or hydrophilic, you have totally different immersed front, which may totally change the propagation or not.
Well, we definitely didn't try that. I would say that at 50 megapascal compression of the fluid, surface tension of the fluid would play a secondary role, but I can't do the math right out of my head. We didn't consider that. I'm assuming it's negligible, but maybe I'm totally wrong. I don't think it's relevant here.
I suppose it's a little bit relevant because, especially when you're talking about this double or triple nucleations events, I suppose it's related because if it's more super hydrophobic or hydrophobic, the front of the liquid will be more uniform. If it is more hydrophilic, then it's because of the capillary, so it will be like a lot of finger. The liquid finger will totally change the distribution of the front, the stress of the front. So I suppose maybe it's related to how this double or triple nucleation happens. Okay, this is just my comment.
I need to think about that. We totally ignored any of that. My intuition was that at such high pressures, only the viscosity matters and the expansion of the fluid. Maybe I'm wrong.
Thank you. Thank you.
Jay, go ahead.
I'm probably wrong, but I keep getting this feeling that I'm seeing Unitian rice here in a funny guise. You know, it's not. Usually, you think of these nucleation fronts in those contexts as being slow. But here it's a very strange geometry. I would think of looking at Unitian rice in the context of tension and seeing if you can come up with something interesting. Because it looks like, you know, you're sitting inside the cohesive zone, you're creating a propagating island.
No, 1 second. So you sit in this cohesive zone only at extremely low viscosities, right? So yeah. Most of the results, the jump size much larger than the cohesive zone, right?
But those you don't have high enough frame rate to see what's going on anyway.
No. Why? I'm sorry.
These simultaneous events are also for the for high delta lambda.
So it's a continuous transition. So the typical example that I showed you, where you have a single event, is and jump amplitude of 3 millimeters or so, are 400 centipoise. So this example I should have wrote is 100 centipoise, and the two other examples are 1 centipoise. So growing from 400 to 100 centipoise, you start getting 2 events. Going even lower, you get 3 and more.
Still, I mean, your whole model, your whole picture is to cause, at least with the numerics, to cause a small nucleation site in a region that's supercritical. It's larger than KC.
Exactly.
So it kind of feels like Unishi Rice kind of scenario. That's all I'm saying. It's not. It's obviously not the same thing.
No,
It's not-
I know what your point. I know where you want to go with that. So I think you're absolutely right. So at the beginning, right, we
taught you well.
initiate.
That's what you're supposed to say after I say anything, and then you tell me why I'm wrong. But okay.
So at the beginning, Gabriele did exactly that. So he induced a patch. How large should the patch be? It's he checked some trial and error, and took the smallest patch that you need to induce for self-sustained propagation. So the patch is somewhere here. It's a sub-millimeter, but once you go out of the patch, so patch is localized, couple of millimeters, but once the crack, at the 3rd time step, the crack is in all dimensions is already much, much larger. So you're absolutely right. For example, you can find here an acceleration of the transfer velocity. These must probably do depend on the cohesive zone properties, the size, and your nucleation patch. But I think what we are focusing is the later time when all dimensions of the crack are already much larger than the patch, and the size of the patch at that time is irrelevant anymore. So what Gabriele checked is that if he doubles the size of the patch, the later behavior of the crack is very similar. So the Unishi Rice is extremely important at the early stages, maybe even to explain the acceleration, but I think it plays a secondary role at later times.
No, I was just more thinking of also these multiple nucleations, which feel in that sense like Gunishin rice, but it's not the same thing. You have to play with it, I guess. But I think it's a reasonable, it's a nice picture to maybe push, but I'm not going anywhere with it because I've given you all I know. So
Good.
Let's come back to that. Seraphim, please go ahead. I don't hear you. Do other people hear him? Maybe you have to select the different microphone. Seraphim, it says that you're unmuted. At the lower left, there is a selection of the microphone that's possible. Okay, working on it. Someone else wants to ask a different question, take us in a different direction for a minute. We'll come back. Or we can just wait for a minute.
Do you hear me now?
Yes, go ahead.
Ah, perfect. Sorry for that. Okay. First of all, thank you very much for the presentation. It was very interesting. So it was so interesting that I decided to participate a bit in the discussion, even though I'm not sure that my reasoning will be relevant, maybe a bit naive, but still. So I have a question. First of all, maybe I miss it, but do displacement was the same for different viscosity, for different liquids with different viscosity in the experiment?
So by displacement, you mean the jump amplitude?
No. I mean, then, okay, if I understood well the experimental setup, you control displacement of some. So you don't control pressure, you control displacement. So you apply this displacement to the liquid, then that push liquid inside the sample, and then you observe a crack propagation.
I see.
And
yeah, so you're not you're discussing the displacement of the pump.
yes, exactly.
Yeah, there is slight variation. I don't have the results right now. There's slight variation on the injected volume. And there is also a slight variation on the initial pressure. But they are second order. We were not able to make sense out of that. Maybe we should, but
so we could consider that it's like same rate, so it's same magnitude. For
the rate was kept constant. The displacement rate. The only thing that we can say for sure is that Thomas was driving the pump at the same rate.
Same rate for different viscosity.
Exactly.
Okay. And this gives me an idea. Maybe I'm wrong, but if we have the same rate for two liquids with different viscosity, it in some sense it will change the amplitude of pressure increase because it's proportional to viscosity. And if we will consider the system from energy point of view, that means that each time when you push this pump, you feed energy to the system, but amount of energy which you transmit nearby this tip will depend on viscosity, and that's why you have like different jumps amplitude. So that's why for water you have smaller jumps, because it's like, let's say, you better discretize the energy which you transmit to the system because of lower viscosity. But with high viscosity, your, let's say, discretization higher, so you put more energy than needed, and that's why you have bigger this cracks, and that's why you have this like unstable jump.
We should sit down together. I would be happy to. I think what you're saying is very similar to what we have in mind here, right? When we try to explain the model, this is exactly what we have in mind. The larger the viscosity, the higher the pressure you need to apply. The higher the pressure, the larger leg you need to keep the same Kc. So I think we are on the same page here. Once you dictated the lag, I think the model that explains the jump amplitude is there less like it's more straightforward. It's obvious that the obvious. I'm not sure if obvious, but I think we are pretty confident that the larger the lag, the larger the jump amplitude. So I think it sounds to me that what you have in mind is very similar to what this model was trying to accomplish. Higher viscosities, higher pressure you need to apply, meaning that you can nucleate a crack with a larger leg.
Okay. Thank you very much.
I was going to follow up on that really interesting point and say, I'm probably missing something obvious, but it feels intuitively like the effective compressibility of the fluid should matter too. So that when you have a very small fluid volume for the essentially the same viscosity, you have a higher compressibility, so a much easier chance of pushing it out to the crack tip as the crack tip extends.
So 1 second, let me understand. You're asking about the difference in compressibility for different viscosities.
And for different crack dimensions, for different volumes of fluid that are in the crack.
So the crack dimensions matter. This is absolutely right. The answer to that I'm a bit cheating in a sense that the analysis has been done in a specific region or in a range of radii. So the sample is I don't remember, is something like maybe 10 centimeters. So we focused at the middle with the range of a couple of centimeters. Don't go too far away, and so the length of the crack is important. So it's the analysis, the radius comes in here explicitly. So in order to compare all these results, the only way to rescale everything if R doesn't change much. This is the answer to that. So you might need to repeat the analysis if you now have a 1 kilometer crack, say, or something like that. I think the framework is the same, but the numbers will differ. And regarding the compressibility, the quick check that we did between the difference in compressibility between pure water and pure glycerol, or some mixture of the two, didn't make any difference to our result. And the third point, which is extremely important, is of course that we are focusing on several jumps of the crack, meaning that the assumption is that the pressure doesn't drop significantly in these intermediate events. If you wait very long, of course, the pressure will almost reach zero. So we are focusing somewhere in between, just because we don't know how to calculate the pressure. So we need to assume it's constant between events. So all the results that we compare, we made an effort to analyze the results points where the fluid diameter is the same. So we kept the fluid diameter the same and analyzed the jump amplitude at the lag of the corresponding crack. So pretty much the occupied volume was kept constant.
Gotcha. Thank you. Someone else has another question? Yeah, go ahead.
Yeah. And just maybe side question, and the rheology of the liquid which you use, it's
Newtonian.
Newton. Okay.
Glycerol, glycerol is Newtonian entirely.
Yeah, I'm sorry.
So
Just
base weights, I don't know if it's allowed, but they are making really, they are getting really amazing results where they now use nonlinear fluids. Really nice results.
Someone else has a point they want to bring up? Question? While you're thinking about it, let me ask one or two more questions, because can you go back to the data that show velocity as a function of jump amplitude? And also there was another plot.
Velocity versus jump amplitude. Good.
Yeah, this one. Yeah.
Can go show with the simulations.
Yeah, right, that one. And yeah, I'm just really curious about what happens here for tiny jump amplitudes, and it makes sense, like you say, well, once you're kind of at the small, within a dimension that's similar to the cohesive zone size or something, then there's probably interesting things are going to happen. But in the plot you show, I forget, it was one or two back from here or in front of here, you showed time as a function of, you showed the sort of acceleration of the
yeah, here it is.
So, yeah, wait, I mean, here in 20 microseconds, if you're going at that speed, I guess 20 microseconds at a kilometer per second is like you've gone 2 centimeters already. So it's huge. But maybe, yeah, like this fraction of a millimeter doesn't seem like it shows up on this, but maybe it does, just because you're not going at a kilometer per second, you're going at a much slower rate.
But this is the transfer direction, right? So I think the idea is that the radial expansion of the crack is still within the cohesive zone. So when the crack finishes the jump, it's still within the cohesive zone size. And while you're absolutely right, in the transfer direction, you can assume that you run out, but the crack itself is still within the cohesive zone. Now, as a naive argument would be that according to Jim Rice and the co-workers, you can estimate the stress intensity factor very far away by integrating with some kernel the curvature. So meaning the more curved the crack here, the higher stress intensity factor it imposes to very far away, something along these lines. So maybe that failed, or this should be corrected to some extent when your crack is still within the cohesive zone. This is what I'm thinking about. But I cannot. I don't know how to make any better argument.